So, now turns out this is an interesting thing about impulse responses, that there are alternate representations also possible. Okay. So, what we derived a closed form solution, right, and moreover I just want to show you one thing. If I want to plot this function over here, what will it look like? So, let us just plot it over here, right. So, this is my x axis and let us say this is x prime, okay, this is my 0. So, for x less than x prime, what does it look like? Both are straight lines, the slope is negative or positive? Negative, because x prime is less than L. So, it is a line that is going down like this, right. The other term, so the other term x prime and x minus L also negative, x is less than L, but it is a straight line again and the slope of the straight line is, right. So, it is, but it is going to be positive, right. So, it is going to be a increasing function over here. Does that look right? Everyone agrees? So, you can do a check, put x equal to x prime, what do you get? You get the same relation on both sides and it is a negative quantity, right. So, that is what you get over here. Alright. So, this is, I have got a continuous looking function out of this, right. There is no singularity in G, but look at G prime. G on both sides it is continuous, but look at the derivative of G on the left hand side and the derivative of G on the right hand side. The discontinuity is in the derivative, right, which we sort of saw in this relation. The derivative was discontinuous. Okay. So, looking at this, looking at the solution that I have got over here, you can see it is continuous. Can you say therefore that it has finite energy in this way? There are no kinks running off to infinity, finite energy, right. So, finite energy signals also they are square integrable. So, what is a nice property of square integrable signals? Again we studied this in signals and systems. It is over a closed domain 0 to L, right. So, what is one possible way of writing this G? Can I write it as a Fourier series, right? Over the domain 0 to L, the signal has finite energy, it should be representable by a Fourier series. What is Fourier series? Linear combination of sines and cosines of different frequencies, right. Now, in this case frequency is a spatial frequency, right. The string can be like this, it can be like this, or integer multiples like this, right. So, this is my 0 and this is my L. Just by looking at the boundary conditions, can you say something about which terms will be 0, non-zero? Exactly, they will only be sine terms, because cosine terms will have non-zero amplitude at 0 and L. So, I can straight away say that this is going to fit within 0 to L and should be a sine function, right. So, I can write this as in the Fourier series form, n is equal to 1 to infinity a n sine of n pi x by L. Is that fine? So, now on the left hand side I have a function of x and x prime, right hand side seems to be only a function of x. So, where will the x prime dependence come from? Coefficients. Coefficients will be x prime dependent. So, let us write it like this, a n of x prime. Okay. This is the most general possible way of representing it, because it is it is a square integrable signal that I have. Okay. Now, the next step is to find out what are these a n's, right. So, I have a differential equation. So, what can I do? Substitute it. So, what will be the second derivative? So, okay, first derivative of sine will give me cos, one more derivative will give me a sine, right. I can apply it to each of the terms one by one. So, the left hand side will become, summation will remain, n is equal to 1 to infinity, and what should I get? Minus n squared pi squared by L squared a n x prime sin n pi x by L is equal to delta of x prime, right. All of the tricks we learned in Fourier series can be used over here. To find out a n, what should I do? X equal to x prime won't help me. Multiply by what? No, Fourier series. Yeah, he has the right answer. Exactly, right. So, orthogonality between signs, right. So, the relation that I have is that the if I take this, so sin let us say m pi x by L and sin n pi x by L, these two are orthogonal functions on this interval. So, orthogonality will say that this is going to be equal to, so I have done the calculation, you will get L by 2 if m is equal to n and 0 m not equal to n. So, I can multiply both sides by sin m pi x by L and then integrate 0 to L, right. So, what will the right hand side become? So, let us start with the left hand side. What happens to the left hand side? Which term will survive? I am multiplying by sin m pi x by L on both sides of this equation and integrating 0 to L. Which term survives? M, a m, right. So, the left hand side will be minus m squared pi squared by L squared a m of x prime into L by 2, right. And the right hand side is going to give me what? Sin m pi x prime by L. So, I have got my a m, right. So, I have got my a m and then what do? I plug it back into this relation, right. In this equation the only thing unknown was a n's, which I have evaluated now. So, what do I get? This is the final relation, right. So, here you can see that one of the L got cancelled off. So, that is why this is 2 L by pi squared, 1 by n squared was still there. I have a sin n pi x by L and a sin n pi x prime by L, both terms are over here. Okay. So, now you might ask that why should I choose this form? This looks so much more complicated than my previous form over here. Didn't this look much simpler, right? This looked much simpler than this. Okay. So, how do you know, and this will end this module over here with this discussion, how do you know which form to choose? So, this is the series form and that was a closed form. Which form should you choose? Exactly. So, remember the final solution is given here, the integral of g and f. Now, depending on the kind of form of f, one or the other will be easier to evaluate. For example, if capital F were also of the form sin k pi x by L, then that integration is very simple. I can use orthogonality and this integration will be simpler. All the terms will drop out, I will be left with one term, it will be an exact calculation. On the other hand, if I use the previous form, then I have to do the integration of x multiplied by sin x and do all that integration. Both will give me the same answer because it is the same function. Okay. But sort of the take home message from this final slide over here is that Green's functions can have multiple representations, closed form or series. You should choose that form depending on the problem at hand. Okay. Basic idea is we want to reduce the calculations. So, whatever helps us achieve that. Okay. Well, yeah, because this string is in the x coordinates only, right. So, it has to be a Fourier series in the x term only with some coefficients that should not depend on x. So, the only thing remaining is x prime.
So, this summation n equal to 1 to infinity.
Yeah. Oh yes, correct. So this should be infinity. Yeah, thanks for pointing it out. Yeah. And summation over n. Very good. N is equal to 1 to infinity. Yeah, there is no I over here.
Sir,
Yeah.
does that series solution converge to the closed form expression?
It is exactly equal to that. It converges to that.
For what value?
For no value. For the sum of the infinite series is that. Yeah. It's a Fourier series. So if you keep finite number of terms, it is not actually equal to that. But you can see these terms, they begin to decay. There is a 1 by n squared. As you go to higher and higher n, they begin to decay. We will continue our discussion about Green's function. We have looked at 1D Green's functions. Okay. So what I will do now is, before we go to 2D Green's functions, I want to summarize a few general properties that Green's functions obey in general. Okay. So this is the Green's function that we had from yesterday's class, right? So this was, when we plotted it, it looked like something like this. X prime, and this was my x, right? And so there are some general properties that you will observe. So the first is the Green's function. Okay, we are talking about properties of the Green's function. So if I look at the homogeneous differential equation, okay, homogeneous differential equation means the right hand side is 0, right? So this Green's function, it satisfies it, right? Can we say that? The way we derived this function was by looking at, basically we ignored the point x is equal to x prime and we derived this, right? So the homogeneous differential equation is satisfied by the Green's function. That in general is how we will construct it. Okay. Looking at the form of the function, can you say anything about its symmetry properties with respect to x and x prime? If I interchange x and x prime everywhere in this, will I get the same function? Yes, right? Because case 1 will become case 2, case 2 will become case 1, and I will get the same things, right? So it's symmetric with respect to x and x prime. Okay, right. The other thing that we said is that it satisfied in this particular case the, what kind of boundary conditions did we have? The boundary conditions were also homogeneous in some sense. We said the string is clamped at both ends. So it's like a homogeneous boundary condition where the field is displacement is 0 at both ends. So we can say that it satisfies homogeneous boundary conditions. Okay, so 3 conditions. The other condition is we had 4 variables, and the 4th trick that we used to eliminate all 4 variables was that of continuity, right? So we can say that this it is continuous at x is equal to x prime. Okay, is it differentiable?
Satisfies the differential equation at all points other than x dash.
That's the first point, yeah.
Yeah, but it's not everywhere.
I mean, at the point of the singularity, there is a bit of a problem. It's hard to say if the right hand side is infinity. What do you say about the left hand side, right? But we will see in the next example that you will, in some cases, even construct a Green's function which has a singularity in it, and it obeys the rest of the properties also. It will be problem dependent. And yeah, this is the other part, right? It's continuous but not differentiable, right? So we can say that, for example, G prime has a okay. I mean, these are just sort of simple observations you can get by looking at the form of the Green's function that we got and how we derived it. Okay, so it's more like a review or summary of what we've done so far. Okay, so this was the sort of simple case of a one-dimensional Green's function. We didn't have much trouble in finding out any of the constants involved.